done, eh? Okay. Hey, come on. Okay, there we go. Okay. Okay, so dimensional analysis, the flow. Okay, so basically we distinguish between dimensions, as I've just mentioned, the type of thing associated with a measurement, to people, or to length, something about length, or something about time, or what have you, versus the unit, the yardstick that's used to measure it, the particular yardstick, meter versus foot, etc. Now, this dimensional analysis, beginning in the 1700s, people started to realize that when you associate quantities with these units, you can do a lot of really useful things. And the most important thing that I'm going to highlight here is this validating models. And this is not about proving that the model's correct, but it's at least making sure that it isn't obviously wrong. Okay? That you're not adding, for example, a quantity which represents people to a quantity which represents amount of money. Or that you're not adding a number that represents things in meters to another number that represents things in feet. You'll get out a number, to be sure, but it'll be meaningless in both cases. Yeah?
So then actually, let's come back to the paper then. If they're lacking units, zombies versus humans. So like zombified people versus susceptible people, would they be two different units?
Okay, so it turns out that we choose our unit systems, okay? We develop our own unit systems. And we have the privilege of distinguishing what we mean by a dimension or a unit, okay? But what you can do is, if you associate units with things, you may choose to call zombies people, or you may choose to distinguish them. If you distinguish them, you are more likely to catch problems in how you're combining them. Now, you can deal with those problems by having conversion sort of coefficients, like that they happen to be 1-to-1 or something like that. Each person becomes one zombie.
Yeah.
So there's a conversion coefficient that's used. But you certainly don't want to be doing something like assuming that any zombie is a person in terms of how it's counted or something like that, probably.
Right.
So you'd actually want to think, but this is an overview slide. We'll go into these things in a little bit more. But they can be also quite useful for a couple other things, including scoping them and creating the equations in the first stage, thinking through what must this equation look like. Amazing things you could do with dimensional analysis using this. Now, the systems modeling community, and I'll particularly emphasize the system dynamics modeling community, has actually made use of dimensional analysis for some validation of models, and it's always been good at that, and that's based in its engineering roots. But it's really made limited use of dimensional analysis more generally. And I have a particular interest in this because of performance concerns. And it turns out that you can use dimensional analysis to formulate small-scale versions of agent-based models. Okay, but let's take one thing at a time. Okay, so we're going to distinguish here between dimensions on the one hand and units on the other. Okay, just forgive me. Yeah, no, it is recording my voice. Okay, it should be. Okay, so dimensions here are described as sort of semantic category associated with the reference for some quantity. So we have a quantity, to something. Dimensions describe, so what semantic category is this? Is it a length? Is it some sort of pressure? Is it an acceleration? This abstracts away from the yardstick. We're not saying how we're measuring in this particular yardstick or that yardstick. It's saying the sort of thing that it is, right? Typically here, we're not going to have conversions between different sorts of things. We can't have a number, say that's a length, and turn it into a pressure just by dividing it by 2 or something like that. These things are more independent of each other than you say things that are differ merely in terms of units. So a given quantity has a unique dimension associated with it. This is important. Quantity has a unique dimension, given your units, the dimension system you've chosen. It has a unique dimension. Okay? Units describe the sort of the yardsticks, the references used in performing a measurement. Okay? So we can measure things in microseconds, we can measure them in weeks or centuries, a unit of time. And, you know, a quantity can be expressed in many units. We can express it as microseconds or seconds. Same quantity. We can express it. No one is particularly privileged there. And we can convert from one to the other quite readily. If I want to convert seconds into microseconds, I multiply times 1,000,000. I have 1 second, that's 1,000,000 microseconds. But I want to convert between days and weeks, I divide by 7. Convert, right? So it's worth noting that these different units at issue that I can convert between all belong to the same dimension. So when I'm converting between seconds and microseconds, these are all aspects of time. I can't just double it and convert it to an acceleration or something like that, right? So these describe the measurement of the reference. What yardstick did he use? Did he use the Celsius yardstick or the Fahrenheit yardstick? To take this temperature value, the Kelvin yardstick.
0 Kelvin.
Time is frozen. Absolute 0. Okay, so it's worth emphasizing that these are both aspects of metadata. I would say, what dimension it's associated with and what unit it's associated with. It's information about this data. Okay, so you have a 2, you have a 3, you have a 5 in your model, or a 500. That's meaningless without knowing what does it describe, or what sort of standard was used to measure it, and what sort of thing is it? What dimension is it? We can willy-nilly on a computer add together a 3 and a 5 and a 7, even though they're different dimensions, but it's meaningless unless they're the same dimension and unless they're the same unit. Now, it's a lot easier if we have, say, 3 feet and we want to add it to 1 yard. It's very easy to sort of convert that automatically. 3 feet is, in fact, 1 yard. 3 feet per yard. So you can convert the 3 feet to 1 yard, add it, and we get 2 yards when we add it to the other yard, right? But in general, if you have a program or a model which has people flowing into people per unit time flowing into a stock that holds dollars, meaningless, useless. Okay, so these are metadata, and they're metadata that relates to model validity, among other things. But they also relate to other useful things. For example, often when we see a graph of a quantity, we want to know what units is it in. Is the time axis here? Is it in months, years, days, hours? We want to see this sort of thing presented to us. When we see parameter sets in silver, we want to know, is this thing measured in terms of the dollars per year or dollars per month? Is inflation a percent per month or fraction per month or fraction per year? These are the sort of things we want to keep track of, yeah? Okay, so they're critical to our reasoning. Okay, so here's some examples of dimensions, units. This is a frequency, how frequently something is happening. Once per second. The dimension is one over time. Count per unit, per the units, we can measure that in any number of different things. Given something measured in this, we could turn it into this. Or something in that, we could turn it into that. Angle. This is what we call dimensionless. Now, this is actually a misnomer. You'll hear it a lot. Dimensionless. But it's actually a misnomer because it's not like it has dimension, it has no dimension. It's almost like saying something that's of length 0 is lengthless. Something of length 0 length, infinitely. It's not of length, it's not lengthless, it's of length 0. But in English, we kind of mix these terms loosely. So we say this is dimensionless quantity. And we'll sometimes write it as unit, dimension as unit or 1. This is used, by the way, in Bunsen. Or DMNL is also used eventually. DMNL, dimensionless. Yeah. Okay. What sort of things are dimensionless? Well, a fraction. If someone were to ask you, what fraction of this room is covered by tables? It doesn't matter. In giving that fraction, I can say that fraction. I don't need to ask you, well, what do you want it measured in? Square meters? Square feet? Square yards? I don't have to ask you because it's like 50% of the room is covered by tables. It doesn't matter whether I measure it in feet or square feet or square meters. At 50%, right? I can change dimensions. Say, I prefer square meters. And then my origin comes out and I say, I prefer square feet. What's that?
Sorry to interrupt. Did you mean that dimension means areas and you want us to measure in what units?
So the dimension for area would normally be square feet or square yards or square meters. But this is actually a dimensionless thing. The fraction of the room that's covered by desks. That's dimensionless. It's what we call it dimensionless. It means it has no dependence on dimension. I can switch dimensions and it's no consequence. Whether I prefer square meters or square feet or square yards, it's irrelevant because the quantity doesn't have to change based on my preference. If I told you, Yudi, if I asked you to sort of measure the length of this, and you told me, and you'd have to ask me, well, what do you want it measured in? And I'd say, I want it measured in meters. And you say, this is 1.5 meters tall. But if I told you, I want that measured in feet, you'd have to change that, right? You'd have to go from 1.5 feet to something like, 5.5 feet or something like that. If I said I want this measured in miles, you'd have to convert it again. You'd have to change that number. With a dimensionless quantity, you're not going to have to change it. Whatever my preference is for units doesn't matter. It's the same value of the quantity regardless. Do you get that?
So for fractions, just maybe for a point of clarification.
Yeah.
So if you're talking about the square footage, just say for instance, right, this room that is actually covered by tables. So let's say that it's 100 square feet.
Yeah.
Just as a guess.
Sure.
Right. So then it would be say like 25 square feet. Out of 100 square feet. So those units cancel out. And that's why it's dimension 1.
That's right. That's right. That's a kind of operational way to see it.
Yeah.
And what you're getting to, and this is really important, is that there's a dimensional algebra. There's just like we learn how to divide numbers, there's a similar thing where we can multiply, divide, take the square root of dimensions. And it's meaningful. And in fact, there's been some fascinating books written on actually keeping track of this information on a computer. And I don't know if you folks know, but the problems in dimensions have accounted for some major engineering failures. Do you folks know about that probe that went to Mars? I think it cost $800 million to send this, what was it called, Mars Deep Space, no, it's called Polar Orbiter or something. They sent this probe towards Mars. shot it off from the Earth, and it took 3 years to get there, or something, $800 million. And it approached the red planet. It was getting these photos. Then went into land there. Actually, it wasn't the orbiter, it was the Mars Polar Explorer or something. It went into land there. It was in its final phase of landing. They never heard from it again. And there's various speculation. Martian shot it down.
Giant robots got it.
And then it turns out that when they finally found it, part of their software had been operating in terms of newtons, I think, or newtons per second, and then another part of their software was using a library or something where it was in foot-pounds per second or something like that. And they called off their giving a thing in newtons, and it told it, how much acceleration to apply or something. So it slammed into Mars at like 10 times the speed it should have because it didn't convert units.
They're just using the same numbers.
They're just using the same number. They're passing around numbers, but the purpose of computers is not computation, it's insight. And if you don't carry around dimensions, you can do things to computers that, yeah, sure, it generates a number, but it's a meaningless number. To yield meaning, you really want to be sure things have clear dimension. Something like a fraction is dimensionless. Now, dimensionless things are really interesting. They're very interesting because this is where it gets most interesting. Processes in the world don't care about what units we use. Therefore, they have to be operating in dimensionless quantities. So if there's any accurate description of how things work in the real world, it's amenable to description using dimensionless quantities. This is very important because it constrains the models we have to build, okay? But that's getting deep, and I don't want to go there yet. So we can measure distance and length, but we could quantify it in various systems, right?
Hey, Nick, one second, I lied. Is that light years?
That's the lead. That's the lengths they used in China in old times, I think. Okay, so dimensional homogeneity. So adding items of different dimensions is semantically incoherent. It reflects a deep problem with your system, fatally flawed reasoning. If you are adding area to length, I have 1 square foot and I want to add it to something that's a meter, or that's a foot in length. That's just, it makes no sense. Adding time to weight, or adding, the viscosity to loudness or something like that. Furious green ideas sleep brightly or something. Have you ever heard Chomsky's quote? No? Okay. Semantically nonsensical sentences that people can say. This is semantically nonsensical. We can do the computation, but it's meaningless. And we don't want our models to be doing that. We want our models to be meaningful. Okay? Adding items of different units, but the same dimension, is semantically sensible, but it's numerically incorrect. So we add a foot to a meter. What we're trying to do is kind of meaningful. We're trying to add 2 lengths. But to do that, we need to convert one numerically to the terms of the other, the yardsticks of the other. Okay? We need to convert the meter to feet or something like that. Does that make sense? Okay. Now, by the way, for those from computer science background, you can do type systems. So you've seen type systems. You attach types to quantities, right? We do this in computer science a lot. We attach, this is a double, this is a float, this is an integer, this is a Boolean, this is an instance of this class, eh? We can do a similar type system for units and dimensions to protect ourselves. And there's actually a very nice theory on how to do that. People left it underexploited. Okay, now, we may end up doing this for 2 months. This is such fun. Okay, at least for me.
Very helpful too.
Oh, I'm delighted to hear it. It's always good when the two come together. Okay, so dimensional quantities. Quantities that we measure from the world, or that we believe represent things in the world, or are used to sort of describe how things are in the world. Think in simulation, for example. They can be thought of as a pair, where we have the value. This is a value from real numbers. And this, which is basically a description of their exponents with respect to different dimensions, okay? Forgive me, I'm going to go into a couple examples I think it will make it clear, okay? So we can represent a quantity's dimensions as sort of in two ways. We can represent it as sort of powers of some reference dimensions or units. So can anyone read this for me? What does this say? If L is liters and T is time, what is this? Yeah, this is cubic liters of water, and it's a measure of volume per unit time. So you can quantify the flow of the South Saskatchewan River using this. You could also do it in terms of cubic gallons per unit time, cubic meters per unit time, or other quantities. Actually, I'm saying cubic meters, you have to make an assumption about temperature. But so this is because there's this conversion between sort of cubic centimeter and microliter the same at room temperature, so that I can't remember what it is. Okay, so this is cubic liters per unit time. Cubic gallons per unit time could be another one. This is rate of water flow. Here we have some units to the third power. If it were just this per unit time, that would be like how fast, right? How much the distance is running. I drop in my hat to the South Saskatchewan River, and I see how fast it flows. Okay, that would be length per unit time. It's flowing some unit length per unit time, 1 meter a second. It's flowing down towards Hudson's Bay.
Just a question, why did you put -1?
Okay, that's a good question. So what that means is, I'm going to say people can't see you here, but if it's a -1, exactly, it's dividing by it. So if you have 1 over t, that's t to the -1. If it's 1 over t squared, it'd be t to the -2. Does that make sense?
Yes.
So another way to put this would be length cubed divided by t. Okay? Yeah, okay. So this thing here is sort of the per, as it were, per unit time.
That rhymes.
Okay, so again, if this were just measuring speed, it would be length per unit time. But here we have sort of amount of water per unit time shooting down there in the middle of the river, and we have amount of flow per unit time. Okay. Now we can also think about this in a vector space. Here's powers of length and powers of time. So here, this would be, okay, so this is time, this is length. Where would cubic meters per unit time be on this? Can anyone tell me? So this is a vector space. A given quantity, its units, can be, or its dimensions, can be placed on here. This is powers of time, powers of length. Let me start with a simpler example. Where would length per unit time be? So I drop my hat in South Saskatchewan, and it rushes on Hudson Bay.
Just above that first little arrow line
Here?
Down a little bit. Now over to the right just a little bit.
Where?
Back. Oh, whatever.
Yeah, It's about that. Okay, so this is 1 unit of length. It's length to the 1 power, which is just length, times time to the minus 1 power. In other words, over time to the 1 power. So length per unit of time. Distance per unit of time. Where would cubic meters or cubic liters or cubic gallons
Off the chart.
per time be? Okay, so where would it be? Is it up here?
Yeah, maybe somewhere around there.
What was the time?
The minus 1
Per unit time.
per unit time here.
Down just a bit.
Yeah.
Down.
Well,
Just a little bit.
Just a little bit down.
You're like, that's like pins it down on the
Meters
dog.
per 0.95 times.
Yeah, which actually you can have, which is interesting.
Well, those are numbers, right? You can-
So this, what would this stuff be? So that's actually velocity. What would stuff down here be? Can anyone tell me? Anyone remember back to first year physics?
Acceleration.
This is acceleration.
First derivative.
Right, so if you have some acceleration, 1g acceleration, it'll be measured in length per time squared, because if you have that over some period of time, for 1 second, that will speed me up by a certain amount. It will increase my velocity. It'll increase my length per time by some amount. So you multiply this times some amount of time, you get length per unit time.
Would that be distance per unit time?
Yeah, or you can call it distance if you want.
Okay.
Length, distance. Yeah. Okay, so that's what we call dimensional space, and it's kind of sometimes nice to think about it. Okay, so the dimension dictates the value scaling that's required for unit conversion. Okay. Now this gets really interesting. Okay. A dimensionless quantity holds the same value regardless of the measurement system. Give me a dimensionless quantity. We talked about fraction of this room or something. Give me another dimensionless quantity. Fraction the day I spend sleeping. I can measure the day in milliseconds. I can measure it in years. Weird as that sounds, I can measure a day like that. But I spend half the day sleeping. Okay, sorry. That's not an accurate statement. But I spend a certain fraction of the day sleeping. And it's not zero, believe me. Okay, so what's another, how about from epidemiology? What's a fraction? Prevalence. Prevalence is dimensionless. Now this sounds weird, but I can measure people and millions of people and hundreds of thousands of people. Per person, it's dimensionless.
Even incidences.
Incidence is not so easy because what's an incidence?
A rate. Rate is unitless, right?
No, actually, because rate is what dimension is involved with the rate? Time. A certain
Also incidence.
fraction of this population goes over per unit time.
Yeah. So like per year, per month.
Per year, per month.
Wait, so real incidence, but it's like how
Yeah,
it's
what
actually
time is that?
calculated.
Oh,
Yeah.
okay.
Right. So it's like how it's calculated. Like it's often assumed that it's a yearly rate, but it's
Right.
not really a rate because it's a proportion. Really.
That's right. Okay.
The real incidence should have actually.
Yeah. So say like course of or the initial incidence flow from susceptible to infective. That's the incidence that has a pre-unit time.
So the incidence rate also has a time dimension in it.
Yes.
A certain fraction per month go over or something.
Yeah.
But also the incident cases are going to have like people per unit time or birds per unit time for Westnile model or what have you.
Yeah. It's sort of a funny thing because often it's anyway.
Okay, so here, dimensional quantities have operations that are related to but more restrictive than for numbers. These are than for real numbers. So we often treat numbers in the computer as, they're just numbers. Add them together, subtract them, multiply them, divide them, take a square root. They're just bits. But if you want to describe things in the world, if you want to describe things out there, and you need to do it consistently, there are certain things which you could do numerically, like add together these values in this structure of memory, which would be not allowed dimensionally. Okay? Which gives them the motivation for maintaining metadata. And for examining models, scrutinizing models. Okay, by the way, so this was a two-dimensional space. Here's a three-dimensional space, right?
So, Nate,
yeah.
I'm sorry just to back up for a second. I think I might have missed something. So,
Yeah?
right, when you were using epidemiology as an example,
Yes.
so incidence rate or not a rate, is it dimensionless?
No, it's not dimensional.
Okay, so I think I was confused. I thought,
Prevalence rate is dimensional.
yes, this is not really a rate.
Right. The prevalence is a fraction,
Yeah, yeah, yeah.
is dimensionless.
Okay, so what did I?
Incidence.
Okay, yeah. I thought I said something, right, because I thought that you were, okay, so it might be dimensionless?
Sorry?
It's just that.
Wait, that what's dimensional?
No,
Sorry.
I actually was confused because it sounded like that you were saying something contrary to what I said about incidence. So, right, where I said it's a rate, because it's, like, cases per unit time.
That's right.
And I thought that you had something contrary to that, so I was confused.
No.
Okay.
No. It's dimensional. I mean, it's not dimensionless.
Yeah, yeah.
It's dimensional.
Okay.
It depends. I mean, I don't want to. I mean, actually, dimensionless quantities are also dimensional, but it's a bad term for dimensionless. They just have dimension 0. Just like something of length that's
Where's dimension 0? I'm sorry, I totally zoned out for a second. What?
okay.
Dimensionless does not mean it's actually in reality dimensionless.
Yeah.
It means that it just has 0 dimension.
That's right. So look, we say something is lengthless
Yeah.
if it has 0 length,
Yeah.
and that's really not true. It has 0 length. It has a length.
Yeah, it's just 0.
It just happens to be 0.
Yeah.
Similarly, dimensionless quantities have a dimension.
It's just 0.
It's
Well, it's
0. It's the equivalent of 0. It's like, and let's connect that to what we just said. It is each of the exponents are 0 for dimensionless quantity,
Yeah.
right?
Yeah.
So,
Which makes them 1.
so
Right, because anything to the 0 power is 1.
yes, and that's why we write it also as 1.
As 1, yeah, okay,
As
good.
1.
Good.
We say it's a unit dimension because it's 1.
Yeah.
So incidence rate is of unit 1 over time.
Yes.
Same as the frequency. Frequency is what people come down here. Prevalence rate, the fractional prevalence, is, quote, dimensionless.
Yeah.
It is dimension 1.
Okay.
Does that make sense?
Oh, yeah. I think something just misfired in my head for a second. So,
Okay.
right, because I zoned out and then all of a sudden I heard that something was dimension 0, and I was like, what? What is dimension 0? And
Yeah.
so I had to backtrack. So I had a ADHD moment.
It's just analogous to something of length 0. Yeah.
Okay.
Okay.
Here's a question.
Oh, there's a question. Yes, Jen.
And
Since here we all talk about the numeric dimensions, so I know there's also some non-numeric ones. So we don't talk about here. For example, like in the mind, there's a dimension like the ethnicity. And under it is different. It is non-numeric ones. It is not an animal.
Oh, I see what you're saying. You're saying it's not continuous. It's discrete, almost.
Yes, but there are also dimensions. But there's no unit for those dimensions. Here we talk about length, about the angle. They are all measurable. We can calculate the sum of them or divide them.
Right. But there are other, you're saying, dimensions that, like ethnicity or sex of somebody?
Yes.
Well, maybe. So I'm not sure I'm going to get a complete answer to your thing, to your comment here, but you could imagine, and this is where it gets...
Wouldn't those be units though, then? Like, say, for instance, sex, male, female, or no?
Those wouldn't be yardsticks by which you measure people.
So she's a male?
No. I think you could treat them as dimensions. You could actually... No, this is... Look, there's no canonical dimension system. There's no inherent dimension system. We create dimension systems that are useful, and we can actually sharpen our analysis by selecting some that are clever, okay? And they can have as few as one. Everything's the same dimension. It doesn't give us much power, but we can treat it that way. Or we can have arbitrarily many dimensions. We can distinguish length in the vertical direction from length in the horizontal direction from length in this way. You could actually distinguish those if you have a reason to do so. Too many dimensions limits the strength, it turns out, of dimensional analysis. Too few results in sort of overloading. You have no distinction between things, zombies and humans or something like that. So we could in our model distinguish things that are male and female as different dimensions. You can't have a male flowing into a female stalk. In my GDM model, gestational diabetes model, we have pregnant stalks representing pregnancy.
Right.
You cannot have a man flow into those stalks.
Right.
Right?
Okay, so...
And we couldn't... But this starts to get to hierarchies of dimension, because both men and women are people.
Are people,
The
yeah.
same unit.
No, I don't think I'm not aware of any theory of hierarchies of dimension. But as a computer scientist, I think about this some. And I would treat them as both being examples of persons, but I think of them as subdimensions of person.
Same person.
Subdimensions of person.
So what about the person? What about
Age.
Age is measurable.
No person.
So age we measured in time.
But their dimension is
Yeah,
they
the
are
years
so
old.
real.
It's per time.
Yeah, so
Yeah.
it is a dimension.
It's a dimension. It's a dimension.
Sex would be a dimension.
What he's saying,
I would say it's a dimension. That you could say that females that this dimension.
Yeah,
Okay.
well,
So I would call it a separate dimension.
yeah, well, ask your father, he's a physicist.
No. So both would be persons, but both could be dimensions, so that
Different dimensions, yeah.
different dimensions. Yeah. That's how I would tend to think of it, but or you could treat them just as both as persons. It's just that if you were to distinguish males and females as separate dimensions,
Yeah.
you'd get extra level of checking in your model. If you wanted to enforce in your model to make sure that you haven't accidentally had males
Mixing with females.
mixing with females in an inappropriate way, you could
That happens all the
Really
time.
good.
you could declare them as different dimensions, and you could do a unit check, and you'd find that this male is being, is coming into the,
Only one, we have stock.
and you could block that male from entering that stock, right? You could recognize.
Yeah.
So, I've never used that in that way, but you could in theory do it. You can choose a dimensional system that meets your needs. And if you don't care that much about adding together males and females, and you don't want to have to worry about needing to convert between them or what have you, you could just treat them both as humans. But by the same token, a Western model, do you want to just treat mosquitoes and birds as animals? No, you probably want to distinguish them, so you don't have somehow a mosquito flowing into a bird stalk. They're different dimensions.
Right, but I don't know that if that quite maps onto the whole male-female thing, does it? I think that's a bit of a fuzzy gray line, but but I don't know. Like
Yeah.
it seems right where birds and mosquitoes are one thing, male and female.
I agree with you, but I think part of what this gets to is the fact that it would be nice to have hierarchies of dimension.
Yes.
Like in the HPV
You know-
model, you don't want males coming into the female spots or anything like that.
That's true. That's actually
Females,
very,
right.
very much the case. There's all these stocks which are females only, and there are all these stocks which are male only, and you don't want them to mix. So it actually could be useful, but it would be nice when you total up quantities, like number of people infected or prevalence in the entire population. It'd be nice if you could add males and females together by treating them both as persons.
Yes.
But similarly, you could imagine a model with West Nile with horses and people, and you want to add together to get the prevalence among mammals. And, horses and people are both mammals.
Right.
So you want the mammalian prevalence. It's just, I'm not aware of anyone who's done this. This is going to take someone to do a master's thesis in a few years, probably.
So dimensions, they don't have to have units sometimes.
Which would take so long.
That's a good point. There may be some things, you don't have to have a unit, right? We just say that this person is a male, and we don't say we measure their male. Well, be quiet, young man. There are ways. Hold your tongue. So yeah, that's true. You could have
I'm talking great capacity. What are you guys talking about? Things usually
moving right along. Okay, so dimensional systems can have one, which would glom everyone in the same dimension or many dimensions, right? We could treat all dimensions as being any dimension, and time, people, we don't make any distinction, but that's less useful. Okay, so dimensional analysis. This is the interesting thing. Dimensional analysis exploits these dimensional quantities, assigning dimensions to quantities to facilitate insight into the external world. Okay, now these are various uses of it. Checking the dimensional homogeneity of the model. Checking that your model isn't doing something meaningless. Either numerically meaningless, adding a foot to a meter, or a month to a year. These things happen, believe me. Or, people per month to people per year. Those can happen. I've seen that sort of thing, or seen it almost occur. Or where you're adding things of different dimension, which is even more deeply, sort of problematic. What would be an example of adding different dimension? A very common error. Very common and very valuable to be able to spot with unit checking. But it's a dimensional error. Can you give it one? Adding a what to a what?
A horse to a human.
Okay, that can happen.
Morning to people.
Well, okay, that can happen, but it's actually much more common than that. It can occur in models of all different characters. It can occur in financial models. It could occur in a model of a municipality. It could occur in a model of a business. You're adding David's seen this before, or comparing
Apples to an orange.
conceptually, but one of the building blocks of system dynamics models from the lab.
A stock and a flow.
Stock and a flow. You add a stock to a flow, or you compare a flow to a stock.
Yeah.
Prevalence and incidence.
Yeah.
Oh my God, prevalence is going down, but incidence is increasing. This is so strange.
So,
Not really.
so let's think about this. Why can't I add a flow to a stock? If I think about it in terms of dimension. So suppose I have a stock of dimension x. What's that flow going to be?
X over time.
X over time. That's a different dimension, folks. Among other things, suppose I change the time dimension of my model. I change it from being, the time dimension from being per year to being per month. Which of those has to change? The flow does. Said people per unit time. Well, the unit time is different, so I got what used to be 10 people per month is now 120 people per year. Does the stock value change that there's 100 people in that stock? Doesn't change. Doesn't change. I change. Why doesn't it change? Because dimension doesn't have a dependency on time. Time is to the zero power there. So we could change how we measure time to zero power. It doesn't matter. It's one. Okay. So cross-checking homogeneity model, key. You can find yourself finding all sorts of problems. Even very experienced modelers can sometimes run afoul of this. Okay, this is built into Vensim. Maybe next time we'll take a look at that. Okay. This is really interesting. You're trying to formulate a formula for something. Sometimes you can use dimensional analysis to say what's got to be in there. What has to be involved? You're missing something in that formula. Construction of scale models. This is something David's seen a little bit of. So I have a model that I want to build for Saskatchewan, for West Nile, an agent-based model. But I don't want to simulate all the mosquitoes in Saskatchewan as agents. Or I don't want to simulate all the birds in Saskatchewan as independent birds.
I'm sure that could run on your laptop.
So how do I do it? I build a scale model of it. It's just like when an engineer wants to mark up a bridge and test it with different loads, the bridge to span the South Saskatchewan River. They build a small model and they run tests on that small model. It turns out this is non-obvious because it's not just you multiply everything by a factor of 1,000, and if you put on a weight of 1 pound here, it will be the equivalent of 1,000 pounds on the actual bridge. It turns out that there's a nonlinear scaling relationship, and we can actually derive that from dimensional quantities. Okay.
I think that would be neat to do with the whole. I think you and I might have talked about this, but say for instance, people making inference, say from animal models, and then maybe scaling up to a human, because there are going to be scaling differences.
There are scaling issues. Have you folks ever heard about the scaling arguments for, like why does an elephant look different than a gazelle?
What's the second one you mentioned?
A gazelle. It's like an antelope.
Okay.
Or why does you ever wondered like why ants? If you've seen like an ant, ant could fall from up here or fall to the ground and just walk away. That's like the equivalent of a skyscraper for us. We tell those guys to really walk away. But ants can do that. What's going on there?
Ants are zombies?
It's gotta be. So what goes on is, so when an elephant grows like that, it's the reason its legs are so thick is its body goes up as the cube. It's got a length, a width, and a height to it. So as the animal gets bigger, its body weight goes up as a cube of its sort of length. So you double its length, it's got to be double as wide and double as tall. At least for a snake, it's a little bit different. And snakes like one-dimensional. But an elephant's like that sort of ungulates like gazelles and so on. They're sort of three obvious dimensions. So it goes up as the cube, and what that means is its legs, they have a cross-sectional area that goes up as a square, sort of the thickness. So it's got to have tons thicker legs to support this body, which is many, many, many times heavier. The ant is very small in all dimensions. So when it hits the ground, it actually has a very small force. Very small. Its mass is extremely small compared to its length. But it hits the ground with extremely small force. Run away. Word only so people. So So scaling, this whole issue of scaling, physics of scaling, but based on dimensional analysis. How do things scale from small to large? What's the principled relationship between the behavior of the big thing compared to the small thing? If I take a pendulum and I shrink it from a small pendulum,
Just push it.
don't be hypnotized, to a large one.
For the period of the increases.
Yeah, how does it increase? That's a scaling relationship. And how, as you have an infectious disease that goes from a small community to a large community, to a much larger thing, how did the dynamics of that change? That's dictated by dimension. Now that's an interesting thing, because a lot of people build models where dimensions are ignored. Okay, so they're sort of scale models and reasoning about them. CNHF is sort of closed form model analysis. You do these calculations. The eigenvalues. You do these calculations of how quickly it's growing. You have a complex formula involving square roots and square. It needs to evaluate to the correct dimension. If it doesn't evaluate to the correct dimension, you've made a mistake. That's really, really handy. It'll just point out to you, yep, you made a mistake. It can't be. This cannot be. I don't care what it is numerically, it can't be because the dimensions are wrong.
So R naught.
R naught, it's a great example. R naught has to be of dimension 1 over time. You do a complex calculation for R naught, the number of people infected by an index individual over the course of their illness. You get an R naught. It's not at the right dimension. Throw it out the window.
Well, like square roots or something.
Yeah.
Right, that square roots that might not.
Yeah, that's right.
So it might not cancel out. Well, sometimes R naught can be, like, I know for some of the West Nile models now, I'm sure maybe the dimensions, balance out, but some of the R naught values for some of these West Nile models actually have big square roots being the formula for R naught, or can anyway.
Yeah, that's true. You can have quite complex things. And that's fine, as long as there's the appropriate dimensions inside the square root.
Right.
But, you have to understand it. Simulation results, does this make sense? It's sort of changing in this way as I double the population or triple the population or what have you. Some factors sort of missing. Yes.
For instance, like if you were doing something like a linear regression analysis,
Yeah.
and you transform a variable, say for instance age is say exponential, but you do some sort of transformation on it. What do you do with it?
Okay, so there's
Well, if it has some,
there's some interesting papers on this that I need. Yeah. Okay, so this is really interesting. So let me ask this. I'm going to ask you a question back.
But then I'll ask you a question.
So suppose I have quantity A and quantity B, and I add them together. What does that mean about their dimensions?
Well, they should be the same.
That's right. Okay. Suppose I have what's called a transcendental function. Can anyone give me an example of transcendental function?
Well, I know what a transcendental number is, but I don't know what a transcendental function is.
Okay.
So pi is a transcendental number.
That's correct, yeah, that's true. What's a transcendental function? Well, a transcendental function would be something like sine, cosine, log, hyperbolic, sine. These can be expressed in other functions, but it requires an infinite series of things.
Oh, right.
Okay?
Yeah. So hence pi being one of the indeterminates.
Right. Right. That's true. So, does anyone know how to write e to the x? Does anyone know how to write e to the x? If I didn't have a function e to the x to name that thing, the x function, if I didn't have a name for it, I've given it a name. In math, we've given it a name. How do I write it out? Could I describe it?
Taylor series.
Okay. So it's a Taylor series. So what is e to the x? It's a Taylor series. 1 plus
1 over
x plus x squared over 2
Yeah, right.
factorial plus x cubed over 3 factorial. How do I know that? How do I know that's
I read it in the calculus textbook.
Well, there's a better reason than that. There's a better reason than that. What is the derivative of e to the x? dx.
It's EDX.
Yeah, you got it. So if I write it out, it has to be the case that the derivative of that long expression is itself. That's really interesting, sort of a self-similarity. So 1 plus x squared over 2. Let's just think about that. If I take the derivative of that, what's the derivative of 1? What's the derivative of x? What's the derivative of x squared over 2?
X squared over 2.
Derivative of x squared over 2?
What's the name? Okay, so you have to throw x over 2 there. No, it works that way.
Derivative of x squared over 2? Going once? Going twice?
Oh, long time ago. Was it 2x minus 3?
No. Derivative of x squared over 2?
Minus 1.
What's the derivative of x squared?
2x.
Okay. So it's 2x divided by 2, which is x. Yeah.
Oh, right, you changed.
Yep. So if you have derivative of a constant times a function, it's just the constant times the derivative of the function. Yeah. Okay. So if you have e to the x, the derivative of that is e to the x. You see that? It's a thing of beauty, folks. Man, I hope you don't die before realizing that. It's a thing of beauty.
I'll tell you something about it, I'm realizing that.
I said, I hope you don't die before seeing how beautiful that is.
What is what?
The derivative of e to the x is e to the x.
Yeah.
It's itself. It's the eigenfunction of the derivative operator.
Yes.
Oh, it's just got such beautiful symmetry to it. It's utterly beautiful, and this is very important for certain types of analysis, that derivative is true. But the important thing here, look folks, so if you are taking transforming a variable, and you have e to some other variable, when is that meaningful? So if e to the x is 1 plus x squared over 2 plus x cubed over 3 factorial over another 6 and plus x to the 4th over 4 factorial. When is that meaningful? What does the dimension of x have to be? I'm adding together 1 with x squared over 2 with x cubed over 3. What does the dimension of x have to be meaningful? It has to be dimensionless. Because otherwise, if you have a dimensionless quantity, its square is also dimensionless.
Right. Oh, right.
And its cube is dimensionless.
As you said, we have to think a little bit on all of the really interesting properties in life are dimensionless.
That's right. Whereas if let's suppose x is of dimension time, let's suppose, then e to the x is not defined. It is meaningless because I'm adding something that's 1. Let's ignore that. To an x, which is of unit time, plus x squared over 2, which is of unit x of t squared. So I'm adding something of unit time to time squared. Similarly, if x is measured in length, it's a length. Then I'm adding a length to a length squared. Wait, in the area?
So,
Bad stuff.
well, then I have a question then. So then if you are, say if this is age that you transform, well then, what would the units of your regression parameters have to be? Do they have units? Do they have dimensions to actually balance that out? Like say for instance...
Say that again?
Okay. I'm thinking that if you have some sort of outcome, right? Let's say number of cases
Yeah.
of some sort of disease.
Yeah.
And we're looking at a linear regression model that has age and gender in it, for instance. Do those regression coefficients, beta 1 and beta 2,
They have to have a dimension.
they have to have a dimension that cancels everything else so that they have
Yeah.
people, right, so that they equal people, right,
Right.
essentially, right, because Y equals
That's right. That's right.
Okay.
So you're going to have these coefficients, which are the appropriate dimension to convert it to the right thing.
Yeah.
Yeah. You have to. And now this is really important. Okay, this is really important because that what's hidden is the fact that often that those have a dimension. And therefore, they will be different if you change the units you're measuring things in. If they are in a dimension which is something per year, or something per person per year, or whatever, now if you go and you change your time unit, those coefficients have to change. That numeric value has to change to reflect that. Whereas if you just treat them as some sort of dimensionless number, then you don't see that. And you go and you change dimension, you just apply this regression model. You get meaningless
So
stuff.
with the same coefficients, right, where you're
Right.
changing the unit typically the numeric value. Right, okay.
You just treat them as numbers. That's when we get into trouble. That's when the Mars explorer slams into Mars. That's where you apply these numbers that were deduced with one set of units illegally in a different set of units.
So that's never taught, right, in any sort of, stats course.
Well, it isn't taught in economics. It isn't.
Well, no, I
taught-
know. Right, so any...
Yeah. Where this is taught is basically in the physical sciences and engineering. That's sort of where these things are taught. And even there, they're sometimes taught sort of just as an aside. Like, okay, we keep track of these things like
Keep
that.
track of your units.
Yeah, you keep track of your units, and it's sort of just a side remark. But it's amazing what you can do with units. If you're serious about units, you can figure out what must be the underlying expressions explaining some phenomena and so on. I mean, it's really quite amazing. You can figure out how it must scale to a larger system. How this outbreak, maybe, given how it behaved in this small case, how might it behave in New York City? Something along those lines, with certain assumptions in place. Anyway, I think we've gone long enough today. I think we've kind of overloaded people. So I think we should continue on this some other time. What do you think? And we'll talk about how you actually, at a practical level, do this sort of unit checking in Benson.
Is that just the one button?
One button.
Or two buttons actually control you, right?
Yeah, but you got to fill in the units for the different variables. You got to fill
Units
in.
A-OK.
It'll say units A-OK.
Yeah.
That's right. Now, mind you, any logic has no unit checking right now.
Uni's got to be on that. Uni's next project.
No, but it is something which, if you have something like silver, which maintains units, you can in principle start to do an analysis involving any logic, how these units are used, You can also, with Java type systems, people have done experiments, like Sun, in fact, had a group working at one point to try to capture units in Java, for example. Like Java classes, like actually you have a class. Because you can imagine having a class for a quantity. This is, per unit time, and this is people, and this is whatever. And you add them together, they can be conversions between certain things, etc. Anyway, it's an interesting idea. So this provides some background, but we're going to look at how the nitty-gritty of how this can be applied in Vensim
Nate, don't forget to turn off the recording. Good sir.
Oh. Yep.
Still recording?
Stop.